Hello, everyone. Welcome to our podcast, where today we'll be diving deep into the VibeVoice technical report from Microsoft Research. Are you ready to explore the next frontier in long-form, multi-speaker speech synthesis?
Absolutely. VibeVoice is a fascinating model, and I'm excited to break down its innovations, architecture, and results. To start, can you give us a high-level overview of what VibeVoice aims to achieve?
Of course. VibeVoice is designed to synthesize long-form speech up to 90 minutes with multiple speakers up to 4 at a time. It uses a next token diffusion framework, which is a unified method for modeling continuous data by autoregressively generating latent vectors via diffusion. This is a significant leap from traditional TTS systems, which often struggle with long, multi-speaker conversations.
That's impressive. I noticed that the report mentions a novel continuous speech tokenizer. How does this tokenizer differ from previous models, like encodec?
Great question. The VibeVoice tokenizer achieves an 80-fold improvement in data compression compared to encodec, while maintaining comparable performance. This means it can process long sequences much more efficiently, preserving audio fidelity and boosting computational efficiency.
So with this tokenizer, VibeVoice can handle much longer audio contexts. How does it actually process the input to generate such long and natural-sounding speech?
The process starts with user input, which includes both voice prompts and text scripts. These are concatenated and fed into a large language model, such as Qwen TID.5. The LLM interprets the context, including speaker roles, and predicts hidden states. These hidden states then condition a token-level diffusion head, which predicts acoustic VAE features for speech segments. Finally, an acoustic decoder reconstructs the audio.
That's a streamlined pipeline. I'm curious about the diffusion process. How does the token-level diffusion head work in this context?
The diffusion head is optimized to reverse a forward noising process. During inference, it starts with a random Gaussian noise vector and iteratively refines it to predict the target acoustic VAE feature. This denoising process is enhanced using classifier-free guidance, which interpolates between conditional and unconditional predictions, and is accelerated by efficient samplers like DPM Solver++.
It sounds like the model is both powerful and efficient. The report mentions two separate tokenizers, acoustic and semantic. Can you explain their roles?
Certainly. The acoustic tokenizer is based on a VAE architecture, specifically the TS-VAE variant, which helps prevent variance collapse in autoregressive modeling. It encodes the audio into latent vectors, achieving a 3200x compression rate. The semantic tokenizer, on the other hand, focuses on extracting deterministic, content-centric features using ASR as a proxy task. Both tokenizers work together to provide hybrid speech representations for the model.
That hybrid approach seems to be a key innovation. How does the model handle the input representation for multi-speaker scenarios?
The input is a concatenation of voice font features and text script embeddings, interleaved with role identifiers for each speaker. For example, you might have speaker 1, Z1, Z2, speaker N, ZN plus speaker 1, T1, speaker T, speaker N, TN, where ZN is the acoustic latent representation and TN is the text script for each role.
That makes sense. Now let's talk about the model's scalability. How does VibeVoice perform when scaling up the LLM from 1.5B to 7B parameters?
Scaling up to 7B parameters brings significant gains in perceptual quality. The larger model delivers richer timbre, more natural intonation, and enhanced transfer capabilities, including cross-lingual applications. This scalability is crucial for generating high-quality, long-form conversational audio.
Speaking of quality, how does VibeVoice compare to other state-of-the-art models in both subjective and objective evaluations?
In subjective evaluations, VibeVoice outperforms both open-source and proprietary systems in terms of preference, realism, and richness. For objective metrics, it achieves lower word error rates (WER) and higher speaker similarity scores. The 7B model, in particular, excels across all metrics, maintaining high fidelity even at ultra-low frame rates.
That's quite an achievement. The report also discusses evaluations on short utterances. How does VibeVoice generalize to these benchmarks?
Despite being primarily trained on long-form speech, VibeVoice demonstrates strong generalization on short utterance benchmarks like the seed test sets. It achieves competitive WER and speaker similarity scores, and its low frame rate reduces the number of decoding steps required per second of speech.
Let's delve into the technical details of the acoustic tokenizer. How does it achieve such high compression rates without sacrificing audio quality?
The acoustic tokenizer uses a hierarchical encoder-decoder structure with modified transformer blocks that employ 1D, depthwise causal convolutions for efficient streaming. 6 downsampling layers achieve the 3200x compression rate, reducing the frame rate to 7.5 tokens per second. The training objective follows the DAC framework, ensuring high-fidelity reconstruction.
And what about the semantic tokenizer? How is it trained and what's its main function?
The semantic tokenizer mirrors the acoustic tokenizer's encoder architecture, but omits the VAE components. Its main function is to extract content-centric features, trained using ASR as a proxy task. During training, its output is decoded to predict text transcripts, aligning the encoder's representations with textual semantics.
That's a clever design. Now let's talk about the training process for VibeVoice. What strategies are used to optimize the model?
During training, the pre-trained acoustic and semantic tokenizers are kept frozen. Only the LLM and diffusion head parameters are learnable. A curriculum learning strategy is employed for the LLM input sequence length, gradually increasing from 4,096 to 65,536 tokens. The guidance scale is set to 1.3, and the iterative denoising step is 10.
That progressive approach likely helps the model handle longer contexts. How does VibeVoice perform in terms of audio reconstruction quality, especially at such high compression rates?
The model's acoustic tokenizer achieves leading scores in PESQ and UT-MOAS on both the LibreTTS Test Clean and Test Other datasets. This demonstrates its ability to preserve high-fidelity, perceptually excellent audio even under aggressive compression, which is essential for scalable long-form synthesis.
Let's discuss the subjective evaluation in more detail. How was the human evaluation conducted, and what were the key findings?
The subjective evaluation involved 24 human annotators who provided mean opinion scores across 3 dimensions: realism, richness, and preference. The test set consisted of 8 long conversational transcripts, totaling about 1 hour. Each annotator listened to approximately 6 hours of audio. VibeVoice models, especially the 7B version, consistently outperformed other top-tier models in all subjective metrics.
That's a thorough evaluation. What about the objective metrics like WER and speaker similarity? How did VibeVoice fare?
For objective evaluation, WER was measured using Whisper Large V3 and Nemo ASR, while speaker similarity was computed using Wave LMM Large. VibeVoice achieved the lowest WER and highest speaker similarity among the compared models, indicating both accurate transcription and natural speaker characteristics.
It's clear that VibeVoice sets a new standard for conversational TTS. Are there any limitations or risks associated with the model?
Yes, the report outlines several limitations. First, VibeVoice currently supports only English and Chinese. Transcripts in other languages may produce unexpected results. Second, the model focuses solely on speech synthesis and does not handle background noise, music, or other sound effects. Third, it does not explicitly model or generate overlapping speech segments.
And what about ethical considerations? High-quality synthetic speech can be misused, right?
Absolutely. The report warns about the potential for deepfakes and disinformation. High-quality synthetic speech can be used for impersonation, fraud, or spreading false information. Users are advised to ensure transcript reliability, check content accuracy, and avoid using generated content in misleading ways. The model is intended for research and development purposes only, not for commercial or real-world applications without further testing.
That's an important caveat. Let's shift gears and talk about the broader impact of VibeVoice. How does it advance the field of TTS and conversational AI?
VibeVoice represents a significant step forward in scalable, high-fidelity, multi-speaker speech synthesis. By integrating efficient hybrid speech representations with an end-to-end LLM-based next token diffusion framework, it enables the generation of long, natural, and engaging conversational audio. This opens up new possibilities for podcasts, audiobooks, and other applications requiring extended, multi-speaker dialogue.
It's exciting to think about the creative and educational applications. Imagine generating entire podcasts or audiobooks with just a script and a few voice prompts.
Exactly. The ability to synthesize up to 90 minutes of audio with multiple speakers while maintaining high perceptual quality is a game changer. It also paves the way for more interactive and dynamic conversational agents.
Before we wrap up, let's touch on the technical innovations that make VibeVoice possible. What are the key breakthroughs?
The main breakthroughs include the ultra-efficient acoustic tokenizer, the hybrid use of acoustic and semantic tokenizers, the integration of a large language model for context-aware generation, and the use of a token-level diffusion head for high-fidelity synthesis. Together, these components enable scalable, high-quality, multi-speaker speech generation.
And the use of curriculum learning for sequence length, as well as the classifier-free guidance in the diffusion process, further enhance the model's capabilities.
Absolutely. These innovations collectively address the challenges of long-form, multi-speaker synthesis, such as natural turn-taking, content-aware generation, and computational efficiency.
Let's not forget the impressive compression rate of the acoustic tokenizer, 3200x. That's what allows the model to handle such long audio contexts without overwhelming computational resources.
Right, and despite this aggressive compression, the model maintains high audio fidelity, as evidenced by the objective evaluation metrics.
Looking ahead, what are some potential areas for future research and improvement?
Future work could focus on expanding language support, modeling overlapping speech, incorporating non-speech audio elements, and further mitigating risks related to misuse. There's also room to optimize the model for real-world deployment and commercial applications.
It will be interesting to see how the community builds on VibeVoice's foundation. Open sourcing the code and providing demos will likely accelerate progress in this area.
Definitely. The project page, code, and demo are all available online, making it accessible for researchers and developers to experiment and contribute.
As we near the end of our discussion, let's summarize the key takeaways from the VibeVoice technical report.
VibeVoice introduces a novel framework for long-form multi-speaker speech synthesis, leveraging efficient hybrid speech representations and a next-token diffusion framework. It achieves state-of-the-art performance in both subjective and objective evaluations, setting a new benchmark for conversational TTS.
The model's innovations in tokenization, context-aware generation, and diffusion-based decoding enable scalable, high-fidelity audio synthesis for up to 90 minutes and 4 speakers. While there are limitations and ethical considerations, VibeVoice marks a significant advancement in the field.
That's a great summary. Thank you for joining us on this deep dive into VibeVoice. We hope you found this discussion informative and inspiring.
Thank you, everyone. Stay tuned for our next episode, where we'll continue exploring the latest breakthroughs in AI and machine learning. Until next time.
Goodbye.
Goodbye.
To summarize, VibeVoice is a groundbreaking model that enables scalable, high-fidelity, long-form, multi-speaker speech synthesis, setting a new standard for conversational TTS through its innovative architecture and efficient tokenization methods.